I know, I'm back to using my lavalier microphone that I wrote in the community post saying that I assumed it was broken. Hence, assume. So from that last video, I used my old microphone. I think it was, the brand was Rode. And going back, the sound quality just really bugged me. So I was thinking, why don't I just give this another chance to see if it still works. Hopefully it doesn't make that, you know, loud, static, distracting noise that I mentioned. I think that was probably just, you know, one of the worst days, or probably just bad timing, bad luck, whatever you want to say it. But, you know, if successful, then there you go. This video is up on the internet, so that's how you know that, you know, no issues. If not, then, well, we know the history behind that. So besides that, well, let's just wait and see what happens. But anyway, here's today's video. We have a sum, and everything is actually consists of factorials. So we have 1 plus 1 factorial squared divided by 3 factorial plus 2 factorial squared divided by 5 factorial plus 3 factorial squared divided by 7 factorial, all the way on, so on and so forth. So there indeed does exist a closed form to write out this, you know, pattern of, you know, the sums over here. So we just use that, and I'm sure you'll notice that with factorials, give a little bit of a spoiler, that we're actually going to be utilizing the gamma function since they have that sort of relationship. Eventually, using that gamma function, using a bunch of formulas, that eventually we can actually convert this actually to some integral, and it wouldn't be a sum if we don't go from, like, you know, one change to another. So that's interesting from there. But that's basically just the premise on the way we're going to take this on. But anyway, let's actually just jump right in. So suppose that I call this sum S, right? I can actually, to see a better depiction on how to analyze this pattern, suppose I rewrote 1 in the form of a pattern, like just like how these terms were, you know, expanded out. So 1 can also be written as 0 factorial square and then divided by 1 factorial. Then we just rewrite the same thing, 1 factorial squared divided by 3 factorial, add this with 2 factorial squared divided by 5 factorial, you know, so on and so forth. You get the gist. We can actually write this as a sum, an infinite sum, and you're displaying this pattern over here. And what you'll notice is that when we get that this is actually just infinite sum, and our first term starts at 0, then we see that we can write this as n factorial in that parentheses square, and then divided by 2n plus 1 factorial. From there, now let's actually just, let me just actually expand that n factorial square out there. So this is basically just writing the same thing again, but it's just the numerator's just, you know, again, expanded. So n factorial times n factorial, and then divided by 2n plus 1 factorial. So what you'll notice is that we know that, specifically, if we take a look at the gamma function in terms of factorials, we know that gamma of n is equal to n minus 1 factorial. So we actually just do a little bit of, you know, rewriting with the algebra manipulation from these factorials here. We can see that we can write that as the following. So of course, still n equals 0 to infinity. What you'll see is that n factorial can be rewritten as gamma of n plus 1. Then same thing over here. So this will be gamma of n plus 1 times gamma of n plus 1. And then you can also do the same thing for the denominator as well. If we write that using that whole, you know, formula stipulation, you can write this as gamma of 2n and then add this with 2. And so some notes that we want to make, well, not really notes, but more of the formulas we want to use. And indeed, the formula we're going to use eventually is actually the beta function. And that says for any input x and y. So I'll put this as capital B of x, y. We know that this can be written in terms of gamma functions, gamma of x times gamma of y, and then divide this by gamma of x plus y. Then we can actually use its integral representation that says that this is actually just the integral from 0 to 1 of some variable t of x subtract 1, and then multiply with 1 subtract t to the power y minus 1 dt. So just from doing that, we now can write a new s. And so our new s would be that this is actually just, if you look closely, we have that our input is x is n plus 1, and then y is our input for n plus 1. And it would make sense to see that you just add those two inputs together, we get exactly this, which is actually perfect to substitute the beta function. So now we have beta n equals 0. So this will be capital B of n plus 1 comma n plus 1. Then again, just by using that substitution for the integral representation, and so this is n equals 0, and then the integral from 0 to 1. If you do a little bit of, just substitute things carefully, so if you set n plus 1 equal to the input here, so now this time, we would have t to the power n, and then multiplied by 1 subtract t to the power n dt. What I can do here is, obviously we can see that you'll notice that we're integrating between 0 to 1, and then t is, well, it's in between there. But what I can do is I can actually switch the sum and the integral, since it's absolutely convergent. I say this because what you'll notice is that we actually get a geometric series. So geometric series are absolutely convergent. So n is equal 0. Then if I just distribute the t and n over here, so we actually get that this is actually like some common ratio. So t minus t square to the power n, then dt. Yeah, so now applying the geometric series, so now we would have the integral from 0 to 1 of, so this will be 1 subtract your common ratio. In this situation, this will be t minus t square dt. Okay, so now I'm gonna move up here, and so now we would have, if you actually just do a little bit of just distributing the negative and then rewriting or rearranging the terms. So let's say we have the t square actually starts off in our expression 0, 1, then over here we have t square, now it's minus t, and then add this with 1 dt. So now really this just comes out to a simple definite integral, but it's not exactly simple, since you can't really, for one, there's really you can't do substitution, you do any sort of u substitution, and you can't really exactly break this into partial fractions to do so. But what we can do is, if we want to, with this expression of the quadratic function on the denominator, we can actually just complete the square. And so what we do is you just take the second term, divide that by 2, then square that, and then you add that same term back again, so it's like, it cancels each other out from, preserving that equality as well. But after, performing that, this is actually just very simple, so I'm gonna just skip that step. But what it comes down to, you'll get that this is on the denominator t minus 1/2 square, and then add this with 3 over 4. Of course, the numerator is still 1 dt. Now, if I want to do a little bit of manipulation, what I can do is I can actually rewrite the 3, 4, undo that, so there's a square on the, as the exponent. So we have 1, let's see, t minus 1/2 square. Then we can see that just by undoing this, we would have the square root of 3 divided by 2 square. Then we know that specifically, this is actually a very simple form that we take the definite integral, that it actually comes down to the an arctangent formula. The antiderivative is some arctangent function. So we know that specifically we have du of divided by a squared plus u squared. That's simply just equal to 1 divided by a multiplied by the arctan of u divided by a, and then plus c, since this is the rule with indefinite integral. But no worries about that, since we actually have our bounds, so we don't have to worry about the plus c. So just from using this formula over here, we substitute and say that a is going to equal the square root of 3 divided by 2, and then u is going to equal t minus 1/2. Then just all you gotta do is just plug the pieces back together. So now we would have 1 divided by the square root of 3 over 2, just flip the reciprocal. So we have 2 divided by the square root of 3, then arctan of u divided by a, so t minus 1/2, and then divided by square root of 3 divided by 2. Flip that reciprocal, so it'll be 2 times this, and you can actually just easily distribute this out. So this will be 2t subtract 1 divided by the square root of 3. Okay, and then you just evaluate your bounds from 0 to 1. Now, this is actually very easy to see that, so let me first factor out the 2 over square root of 3. And so what I can do is I'll just plug in the arguments, or the bounds evaluated at. So first we have arctangent of 2 subtract 1, which is just, so that would be arctan of 1 divided by the square root of 3. Then subtract and then put 0, so 0 minus 1, so negative 1, so this will be minus arctan of -1 divided by the square root of 3. But these are well-known values that arctan of 1 over square root of 3 is actually just pi over 6. And over here, this is also, well, not also, the arctan of -1 over square root of 3 is actually -pi over 6. So now what we have is 2 divided by square root of 3. So this is pi over 6 minus negative, so now that'll be a plus pi over 6. Add this together, so we have 2 times the square root of 3. What is it? 2 pi over 6, so pi divided by 3. This is simply just equal to 2 pi and then divided by 3 times square root of 3, but we can simplify this out a little further since we don't want the radical in the denominator, as you know, everybody will want that to be taught as. So now the final answer would be that this is just 2 pi times the square root of 3 divided by 9. And so there we have it. We are done. We have found our exact evaluation of the sum that, you know, consists of mainly factorials, and just like that, we are through. So let's just pray that the microphone doesn't make any sort of, you know, loud noises. I hope to. Otherwise, this video wouldn't have existed to begin with. So yeah, that's pretty cool if you ask me.